welcome to Kinematics Lesson 2, Speed and Velocity. Today we will talk about three things: the rate of change, the speed, and the velocity. First, we have the rate of change. A rate of change is how quickly something changes over a certain period of time. This tells you, per unit of time, how much does it change. A higher rate of change tells you that something is changing more quickly, whereas a lower rate of change tells you it is changing slower. A zero rate of change tells you it is not changing at all. To find the rate of change, you must find how much has changed divided by how long it took to change. Our first rate of change we will look at is speed, designated by the symbol v. Speed is the rate of change of your distance, or a measure of how quickly your distance changes. Some examples of speed are found in a speedometer on your car. This measures how quickly your distance is changing in a given time. Another example is a radar gun police may use to check how fast your car is moving. Your speed is the change in distance divided by the change in time. Here, notice we have two monorails moving on the same rope. Since they are attached to the same rope, their distance is moving at the same rate, so their speed is the same. Notice even though this monorail is moving up the mountain and this monorail is moving down the mountain, their speed is the same because the direction does not matter. Since the direction does not matter, this is a scalar. Here we have a change in position divided by a change in time. The units for position is meters, and the units for time is seconds. Therefore, the units for speed is meters per second. Let's try to calculate the speed. What is the skateboarder's speed from 0 seconds to 2 seconds? Well, we know the speed is equal to the change in your distance divided by the change in your time. The change in distance is your final distance minus your initial distance, and the change in time is the final time minus the initial time. In this example, our final distance is 2 meters, our initial distance is 0 meters. Our final time is 2 seconds, and our initial time is 0 seconds. This leaves us with 2 meters divided by 2 seconds, which gives us 1 meter per second. Our next rate of change is the velocity, designated with the symbol v with an arrow above. The velocity shows us the rate of change of displacement, or a measure of how quickly our displacement is changing. Velocity is the vector equivalent to speed. Speed does not need a direction, but velocity has an arrow above the symbol. This shows that this requires a direction. Velocity is found simply by the change in your position or your displacement divided by the time. As with speed, we have displacement is meters, time is seconds, so the units for velocity is meters per second. The difference is now we must add a direction at the end, either forward, backwards, north, south, or any other direction. Direction is signified by square brackets after the units. Recall our monorail example we talked about with speed. These two monorails had the same speed. However, their velocities are not the same. This monorail is moving up the mountain, so the direction would be up the mountain. The second monorail is moving down the mountain, so this direction is down the mountain. Even though the magnitude of the velocity may be the same, since the direction is different, our velocities are different. The direction is a significant part of the velocity. Therefore, this is a vector. Let's try a question. Here, let's calculate the velocity of the skateboarder from 2 seconds to 5 seconds. Remember, velocity is equal to our displacement divided by the change in time. From 2 seconds to 5 seconds means our final position is 7 meters, our initial position is 2 meters. Our final time is 5 seconds, and our initial time is 2 seconds, as shown here. 7 minus 2 equals 5. 5 minus 2 equals 3, so it gives us 5 over 3 meters per second. which is equal to 1.67 meters per second east. Remember, with sig figs, our question has only one significant figure, so our answer must only have one. 1.67 becomes 2 meters per second east. Don't forget about sig figs, and don't forget about SI units. When we speak about velocities, we have two different types of velocities that we may look at: average or instantaneous. An average velocity, also signified with the subscript AV, gives you the velocity of the entire motion. Average velocity looks at the total displacement of the motion. An example of average velocity is the speed you are given at the end of the race. Instantaneous velocity is your velocity at that moment, or in that instant. This is difficult to calculate because in one moment there is no change in time, so the bottom of our fraction becomes 0. An example of an instantaneous velocity is found in your speedometer. Your speedometer of your car does not care how long you have been going at that speed. It tells you how fast you're moving at that moment. To calculate instantaneous velocity, you need to overcome the problem of having a 0 in the denominator of your fraction. To overcome this issue, you must use calculus. For grade 11, we will not be calculating instantaneous. Every velocity we find will always be an average. Let's look at the average velocity. Notice the skateboarder's speed and velocity changes after the fire hydrant. Remember, from the tree to the fire hydrant, we were moving at 1 meter per second. From the fire hydrant, we were moving at 1.67 meters per second, or 2 with sig figs. If we simply take an average of the two numbers, 1 plus 1.67 divided by 2, we will find we have 1.3 meters per second. This is, however, not the correct velocity. The reason why this is not correct is because we are moving at 1 meter per second for 2 seconds, and yet we move faster for 3 seconds. So these two speeds are not equal portions of the total. To find our total average velocity, we must go back to the equation. Our average velocity is our total displacement divided by the total change in time. Here, our total displacement is 7 meters. Our total time is 5 seconds, which gives us 7 over 5, which is equal to 1.4 meters per second east. With sig figs, this is 1 meter per second east, which, oddly enough, is the same as our first portion, which is why accurate measurements are very important. We have now looked at how to find the velocity given a displacement and a time. But what if we need to know the displacement? If we know the velocity and we know the time interval, we can use that information to find the displacement of our object. To do this, you simply rewrite the velocity equation from v equals d over t to solve for d, and we get the displacement is equal to your velocity times your time interval. For example, if a dog runs at 5 meters per second for 10 seconds, how far will he end up? We find d equals vt from our earlier equation. The dog runs at 5 meters per second for 10 seconds, so he will end up 50 meters away. In this question, remember, you must have a direction at the end because this is a vector. So you can add away as your direction. Similarly, we can find the time. If we know the velocity and we know how far an object traveled, we can calculate how long it took to get there. The same as with the displacement, you rewrite the equation v equals d over t and solve for t. You will find the time interval is your displacement divided by your velocity. For example, how long would it take for this boat traveling west at 4 meters per second to reach a beach that is 80 meters to the west? So for this question, like any other question, we take the values that we get. 4 meters per second is our velocity. 80 meters to the west is our displacement. We put those values into the equation and we find 80 meters divided by 4 meters per second. This will give us 20 seconds. So after 20 seconds, this boat will finally reach the beach. This is everything you will need to know about speed and velocity. Thank you for watching.